Now that you are convinced that now that you are convinced that it is very difficult to measure power spectrum, so you have to look beyond the power spectrum. And to talk to you about that, Prabha is here, so she will be taking a 3 lectures.
Let's make things even more complicated. Hey, that's the pointer.
Is there pointer also?
Oh, yeah. Actually, I like the
I don't use. I can't see the point.
power on. I am audible. Okay. Okay, so let us start. So I have been given the task of talking about beyond the power spectrum, but I will explain to you that there are many ways to go beyond the power spectrum, but I will be focusing on these kind of geometrical and topological quantities. Okay. So I think by now you have attended lots of lectures for 21 centimeters, so you are much more knowledgeable than me about 21 centimeters. Okay. So what I'm going to do is a broad overview of how we do data analysis. You have been hearing about the power spectrum, how we infer physics using the power spectrum. So what I plan to do is to give you a flavor of how, instead of using the power spectrum, if you go beyond that, how can we use this physics to infer physics? It need not be only 21 centimeter signals. It can be, so I have been developing it primarily for CMB till now, but I have applied it to large scale structure also and some applications to 21 centimeter. Okay? So that is the broad overview. So let's start now. Okay, so there is a broad plan of my lectures. So I hope that in lecture 1 I will cover, basically I will give a broad overview of how we do the analysis that I just said. Then I will give definitions of these, what I mean by geometry and topology. So there will be some little bit of mathematics which will be done. And the next 2 lectures will be, so this will be just geometry. Next 2 lectures, I hope to first introduce it for random fields. I noticed that in the previous lecture you heard about random fields and so on. So I will describe how we do that. Then I will spend 1 lecture on some work that we have done for 21 centimeter, how we use it for. Then in the last lecture, I will go a little bit beyond. So there is the fields are defined on some manifold of space, 2-dimensional and 3-dimensional. We have seen that. So I will do the little bit more advanced topic of going to 3D and how we study non-Gaussian fields. Okay, so this is the plan. Okay, so let's start with lecture 1. All right, so let's start with an overview of what are cosmological observables. So you have studied in great detail about 21 centimeter signal. So 21 centimeter signal is one of the cosmological observables that we have in the entire universe accessible to us. So traditionally, we started out by studying CMB, I think. Actually, historically, if you look, it will be galaxy surveys. So we had so galaxy surveys. I included them here in collapsed objects because they are compact. Matter has collapsed together and to form compact objects. So historically, you will see these maybe in the works of Hubble and so on. They were trying to map how many galaxies are there in the different sky directions. So you built up a distribution of galaxy in different sky directions. So you can think of that as a random function because you can say, okay, in this direction, let me count how many galaxies are there, and that number in some unit region, sky region, you can think of it as a variable which is fluctuating from direction to direction, and so that is a random variable. Then you have seen 21 centimeter. Then the next one is CFD in different sky directions. We have temperature, or what we basically collect are CMB photons, range, and the intensity varies from direction to direction. So these are all basically the observation that you are doing are collecting photons. Then we also have galactic emissions, which are important for 21 centimeter. We have a lot of, within our own galaxy, we have synchrotron emissions, dust emissions, anomalous, there are various kinds of free emissions and so on. These also, if you look at sky direction, they are fluctuating from place. But one thing you notice in all of this is that the fluctuations, the range of fluctuations vary depending on what is the variable they are looking at, because the processes, the physical process that gives rise to these fields are different. Then in the future, I think we should also have gravitational waves. Right now we have only maybe 90 events of gravitational waves. But in the future, we also expect to have gravitational waves coming from all directions and maybe a mapping. And we can also think of it as a random variable. And maybe neutrinos. That is the set of all. So when I say cosmological observable, the meaning for me is that there is a space and there are values at each space. So there is the underlying manifold and there is a function at every point. So that is the meaning in which I am taking cosmological data. So I'm not interested in those where you are just looking at one direction and maybe line alpha forest you will see at time in different times you take observations and or in different frequencies in particular direction. So that is not what I'm talking about. Though there also you can model as analyses in one dimension. So I'm interested in 2 dimension and 3 dimension. So the first point that we can note is that each of these observables, it is one realization of a field. Okay. So one realization, because we have one observation, and in our observation, in this direction, if there is an overdensity, it is not going to change. We cannot repeat the experiment and say, okay, let me design another experiment where I will get low density. So that's given. The value is. It's a random field. I will come to a little bit later about more mathematical how we define it, random field. But here is a picture just to demonstrate that each of the observables that we talked about, if you take a patch of sky and you plot the values as a color map, this is what typically they will look. The size, so you can visually you can see that there is a certain size of fluctuations, right? At this moment, it is just okay. Some intuitive way our brain recognizes that there is a size of fluctuations, so on, and those properties will change depending on what observable you are looking at. Because the physics that has given rise to that observable will have different impacts in different regions in space, and so particular patterns will be different. So the purpose of my lectures is to talk about how can we quantify. Okay. Then, so if I take a holistic view of the entire universe, the way we have set up our cosmological understanding today is that each of these fields, it originates as primordial fluctuations. For all PhD students or postdocs, so you are quite well aware of this. And so currently the best theory is theory or paradigm, it's not a full theory I would say, is that was generated by quantum fluctuations of the inflaton field during inflation. That's Mukharov and Sito in 1981. This is around the time of Wood's paper, but inflation is 1979 and so on, Sarobinsky and so on developed. Okay, let's take a look at these 4 pictures here. First, look at this. This I just wanted to demonstrate how the physics evolves. You look at this. This is like the fluctuation. This is a CMB. This is a sky. Of course, everybody knows that this is a representation of the sky on the, you cut from north to south and then you paste it on the 2D. So you can see these fluctuations. So this is a time initial time. So let's say this is around the time, this is primordial fluctuation. When inflation ended and fluctuations got frozen, this is how it was. So in some high red regions, we say more matter maybe, and blue is less matter and so on. This is initial. And then after it gets processed, because you start with that and you let physics, the particles and so on interact amongst them by gravity and QED and all those things, then it will become a pattern like this at a slightly later time. And this is something like what we see. But you can see the size of fluctuations. You can already know from here that there is a, I am cutting off the fluctuations at some scale. So inflation says that the primordial fluctuations are really scale invariant, which means that if you look at it as a fluctuation function, and you look at the modes, or you break it up into wave modes, which is because the function can be written as linear combination of different waves. The different wavelengths, they will be equal. That's what inflation is. You let that evolve. Okay. So given such data, or the cosmological data, what can we do? So our goal in studying this entire subject is to understand the universe, which means that we will observe the data and we want to know, we want to infer the physics that the universe has experienced from the past. So we want to push back as far as possible into the past, our knowledge of what happened. So I have split the kind of questions into different parts. For example, we want to know what are the nature of the primordial fluctuation. So the word nature, what does it mean? It means that, so this is my primordial fluctuation. I want to know, is it Gaussian? Okay. So that's one example, one question that we ask. Is it Gaussian? Is it a Gaussian field? And why is it important? It is important because if it's Gaussian, the process by which the quantum fluctuations were generated, there has to be a free field. And if it is slightly non-Gaussian, then that slight non-Gaussianity will depend on that the generating field that should have had some interaction with maybe gravity or something. Okay? And so by knowing the slight deviation from sanity, you will be able to say something about the physics that early. That's why it's important. These are the kind of questions. So we want to know nature of interactions, quantum gravity, and so on. Okay. Then the other is, of course, starting from there, the field has evolved till now. So how do we are modeling this. We use Einstein's equations, and basically we have lots of Boltzmann equations. I'm sure everybody studied a lot of that. We have all those equations, and then we say, okay, there are so many components. For each one, we have an equation, how it will evolve with time. It's a very complicated set of partial differential equations where many degrees of freedom are interactive. We are modeling it by saying, okay, physics is like laws of physics are like we set. So if by doing, so we want to set these up, produce simulated data, of these cosmological observations, and we want to compare them and say, okay, our physics is correct. Then we also have cosmological parameters, which are like the how much matter component is present, what is the rate of expansion that is related to this one. For those parameters, we want to infer their value. There's nothing else that is going to tell us what are they. Then we can also ask test fundamental assumptions. For example, we are assuming that the cosmological principle is valid when we study cosmology. So now we have sufficient data, large amount of data, to test whether this is correct. Then dark matter, what is the nature? Is it warm? Is it cold? And so on. Dark energy, what is it? What is its equational state? Is it -1 or larger than -1? Then is there interaction between them? All of this is what we want to test. The topology of the universe. Is it like just flat R cube, R3 cross time variable? Is it just that? Or is it bounded? Does it curl in on itself? Is it torus? All those questions we want. Then bouncing universe, is it have previous before Big Bang, was there another phase of contraction, and so on. You can also ask at the quantum level, is the space-time that we talk about, that our space-time, is it non-commutative? That means on length scale, which you go to Planck scale, does it become non-commutative? All these questions, you can add your favorite questions and you can expand it. So this is what we want to do. So the question is, how do we do it? Okay, so for that, the first point to recognize is that the cosmological data, the random field picture that I showed, you cannot compare point by point because it's a very, we don't know, we cannot know what are all the physics that happen. We cannot trace particles, let's say a galaxy, we cannot, it's impossible to trace it all the way back to, okay, its initial condition was this, and we want to do it. We can't do that. So because of that, we have to use statistics. So that means, given the data is some function f, on, let's say xyz, 3, or theta phi if it is like the sky data. That function, we want to condense the information and put it in a form which can also be derived from theory, and we compare it. So that's what we do. So what are the ways in which historically we have been doing? So the point is, in the last lecture, you heard a lot about correlation function. You want to look at the data, and you say visually you saw that if a point has a red color, neighboring is also red. And the red color drops out and then it becomes. So that means that there is some coherent length scale. So you want to calculate those coherence. So those coherence are going to tell you what about the interactions that happen. Okay. So that's the quantity. Then we, instead of looking at the correlation function, you can also go to Fourier space or harmonic space and look at the power spectrum. So this is the quantity that has been most widely used now because it's the simplest. Then, so you all know that if a function, if a random variable is not Gaussian, then this 2-point correlation or power spectrum is not going to give you all the information. There's a lot more. How do we access that? So to access that, we can go to higher endpoint functions. So 3-point correlation, 4-point correlation. And there is one way to proceed. If you look in the archive eBay and open, you will see papers in this direction. So that's one way to go about it. Then there are other methods which I don't know much about. Scattering transform I recently saw and it looked very promising, very interesting. So this is scattering transform will be something like, instead of using the wave modes for Fourier space, you use some other wavelengths, okay? Some other basis. So mathematically, it is not difficult. You just use a different set of bases, which will have advantageous properties when you are dealing with the data. The question is all about how do we extract the information better, and for that, guys should look at this method has a shortcoming. Which how can I improve that shortcoming by using a slightly different basis? That is the reasoning with which we look for statistics. Okay, then maybe machine learning. I don't know anything about machine learning, so then the focus of my lectures is going to be this real space. So that means that I will use the geometry and topology of the random variable. And I will, what is the sense in which I define the geometry and topology? This is what I am going to do the next week. There is a big long history of doing this. Even for power spectrum, there is a history. If think maybe it started around 80s. People, I don't know, Prashant, can you correct me? First did this kind of analysis. Okay, I saw some of these papers. So Kaiser's paper, famous paper is there, 1980. It's nice to look back and say who thought of doing it this way first. So there is this history. So here, similarly for in real space, doing geometry and topology, is in my knowledge for cosmology, for galaxies, Doreshkevich had maybe one of the earliest papers. I don't know if they are earlier, but the mathematics was developed by Adler. And there is a big, so BBKS, I'm sure everybody knows BBKS. So BBKS basically translated the maths of Adler for application to Pascal structure. And there are all these papers, and so I joined this team here. Maybe let's go to the okay, so I already said earlier that we need a manifold. So the manifold here is just, it can be R2, two-dimensional space, or three-dimensional space, or for cosmology, these are the two important examples, and surface of the sphere. Because our data, when we look at large volumes in covering large sky directions, we have data on the sphere. So these are the three manifolds which are often to us. And so now first, let me fix a point on the manifold, X, that X. So you all know random variable at X. I'm associating a point. At that point, I have a random variable, let's call it F. A random variable, it will be generated by some physical process. Let's say in this room, I choose this to be my point, and here I'm asking, okay, what is the temperature of the particles? I just small volume, and I say, I assume that it is at equilibrium, and I define a temperature for this region. Okay? And now if you go to another point, that point will have a slightly different temperature. So, so at this point, now I have fixed my point, I have measured the value, I have a temperature. Now 1 hour later, suppose I measure it again, I will have another value. So like this, if I repeatedly measure, I will get different values. So that is a random variable. So at the back of my mind, I will, if it's a random variable, I will have some probability distribution associated with that point. So for all my lectures, I am going to assume that mean is 0, because we can always subtract. And it's I am assuming a continuous random variable, and its value, okay, for temperature maybe is positive. So let for other examples, it can take values from -infinity to plus. That's just what I'm. So to know the random variable, we need the probability. Notice that this is a small, this is normal p, and then we also know we also have n moments. So 2-point variance is sigma 0 square, and I put an x here because it is associated with that point. And I can also define a hierarchy of these. So if I know all of this, then I know my random variable. This is the mathematical. And if it is a Gaussian random variable, f is Gaussian, then you all know that it will have this form, a Gaussian shape. The sigma variance enters here as to the power minus 2. I put it in this form so that I can generalize it. Okay, so this was all done at a say one point x. Now you can, in general, if I do it at another point x prime, these variants need not be the same. Okay, it depends mathematically. Physical conditions, okay. Usually, to proceed or to do physics, we will have to assume yes. So I'm going to come to that. But in general, mathematically, it need not be the same. PDF also need not be there. They can be different random variables at two different. This is the general setting. Now let's come to field. So now my f of x is going to become a field. So how do I define that? First, let me consider n number of points on the manifold. So now you need between the random variable at this point and another point. That information has to be provided to you. And that is what will define the random field. The field is something which has value given a manifold at every point. You have like a function. So that's why I use the this early p to denote. This will basically be, if I consider different x1, x2 points and the random variables at those different points as not independent but different random variables, I will be talking about the joint probability distribution between these random variables. So that is this curly p. So this I did not fix n. It has to be for any arbitrary n. This has to be defined. This is mathematical. Then given this, then we can also define endpoint correlation functions. So 2-point usual to correlation function. This is the correlation function between 2 points xi and xj. Similarly, 3-point you can take 3 points I, j, k and correlate, and they will have a hierarchy of. So when this is given to you, then you can say that you know your field. Of course, when you are dealing with observed data, it's the opposite. You are not given this. You have some field given, values you know, and you are trying to infer it using the data. Different points x coming from. Yeah. So this is the at each of these points x in general, mathematically, you can imagine the random variable at this point has some probability distribution. At another point, it has another probability distribution. So mathematically, they can be different. That's the general case. But in physics, we will assume them to be the same. And what is the way in which you assume them to be the same is this is a symbol. Okay? Because I said now the field f is at every x I have a random variable. At every x I have a random variable. I just use the same symbol to denote that. If you are focusing on only 2 points, you may as well use maybe f1 here and f2, fn and so on. You can do that. Okay, so that is the general definition. Now here by picture I want to demonstrate for you. So this is the same. So the concept of realization. So once you have assigned a value at each x, that's one number. That's for a scalar field, one number. Then the field is, as far as it's concerned, it's a realization, and it's just a function. So you don't have access to the. Okay, so that's one realization. But you can also imagine that if you have another realization, then at the same spatial point, the value will be different. So that is what this is representing. So what for the for the theoretical concepts, what you need is an ensemble of these, in fact, an infinite ensemble of these realizations, and that is what will fully define these brackets. They are ensemble expectation. Okay, so this is mathematics. Is that clear? Okay, just to complete the example, now we have Gaussian field. Earlier we had Gaussian random variable. We have Gaussian field. In that case, the probability distribution function P takes this form. So let's compare with the previous one. So here the capital F is the one-dimensional array of random variables at different x points. So this is the one-dimensional extent. So this is F transpose, and this is the 2-point correlation function. Don't need any of the higher point correlation function. 2-point correlation function, and this is inverse here and F. So if you compare this with the random variable, you have sigma 0 square, sigma 0 to the power minus 2 for the usual random variable, and that is, this is the generalization from that to this. Then here you have 2 pi to the power n. I'm sure you have all worked out multivariable statistics. And there is this determinant of correlation function. Yes.
Can we visualize it in Prof?
Actually, this is a Gaussian field, so I had created this one Gaussian field. But it's hard to say when you look at the field by eye. Hard to say it's a Gaussian. You have to take the values and do a histogram to see if it fits. But to do that, whatever I have described till now, you have to use one more property. That's what I'm coming. So you can do, yes. This is visualization. Okay. So there till there now. I need to explain a little bit more concept. Now I use the word smooth in the beginning, and the word smooth basically means that now that the physical process has been realized, it is infinitely differentiable. That means, what does it mean? It means if I take derivatives of my function, the field f, in first derivative, second derivative, and so on, there will be components depending on what is the dimension of the space we are talking about. These are also random variables. Okay. Then, so similarly at each x, then these f, fi, k, and so on are a set of random variables at the x. But if you consider entire space, then it will be a field. So they are all fields. Then you can now define covariance between these field and the derivatives. Now notice that I'm using a different symbol for this, using sigma, capital sigma. So the C was the correlation between the field at different points. Here, this is sigma is denoting correlation between the field and its derivative. Okay, so it's easy. This numbering I plus, okay, don't pay too much attention. It depends on what is your dimension and so on. So 0, 0 is FF. You can also ask 0 and I, F and Fi, are they correlated? Again, this is ensemble expectation. And so on. All this you can define. Then I want to introduce two symbols which I will use later, and that is sigma 1 square. Sigma 1 square is basically the gradient of f mod square, which is first derivative. It may have 2 components, 3 components depending on the space. So that f mod square, that is sigma. Okay. This is the sum of the variances of the individual first order derivative. Then sigma 2 square, the variance of the second derivative, plus of the second derivative. Okay. So if you will notice that these covariances ij, because they depend on indices, they depend on the coordinate system that you are using. Right? But when you define these sigma 1 and sigma 2 like this, it will not depend on the, it is basically ignoring the coordinate dependence. So sigma 0 square, sigma 1 square, sigma 2 square, important quantities, please note them down, we'll use them later. Sigma, capital sigma is this. Next, so given a field, these spectral properties, small sigma spectral properties, they carry information of a hierarchy of scales that are present in the field. So let's look at them one by one. The first is sigma 0 by sigma 1. So you know that this has dimensions of length, okay, because sigma 1 is the okay. So this Fi is first derivative of the field. I is the component. Depending on the space dimension, I will go from 1 to 1 to 3, and Ik are second order derivative. So it will be 1 2 1 1 2 2 etc. So there are, depending on the space, there are that many number of random.
Capital sigma
No.
At each x.
Yeah, these are all at each x. Everything is at each x.
at 1x we
At
are
1x. Yeah.
not 1x.
No. So that's why I introduced different symbols. The cross correlations are C, the previous symbol. This is at each x correlation between the field and its derivative.
There can be different, say, sigma 0, 3 or sigma 0.
There can be, yeah.
They all have the same information.
I think they will not have the same info, they will have more information. But for the statistics that I am going to introduce up to sigma, actually, yeah, up to sigma 2 sigma. Why I did not introduce much. But there is more information.
So for sigma 2 it is only 1. For sigma 2 it is only 1.
Only one information.
I mean that I plus j can. Crossing to one way.
No. So, yeah, this, don't take this I plus j seriously. It depends on how many parameters are there and how. So this just means that the covariance between whatever Fij is and F. So this I plus j, the counting, I did not write it very thoughtfully. So
It's basically sigma 0 comma ij.
yes, yeah. That is, so it's this, the right hand side is what we should be. So in general, they can be different. No? They can be same. 1 1 is same. So Ij will run over 1 to the dimension d of the space. So if it is 2-dimensional space, both I and k will run from 1 to 2. If it is 3, it will run to 3. Yeah. Yes. So this also Fi, they can be, it will 2-dimensional space. F1 and F2. Yes. Yeah.
Elsewhere,
Yeah. They are not same. Fi is the component, individual, in one direction. This is the average of the two quadrature. Del square F is d1 square F plus d2 square F. So is all points clear till now? X, yeah, I'm assuming X is continuous, yes. So all of this is for continuous X. Real life is not continuous. Okay, so I was talking about the hierarchy of scales. So let's just look at the field, maybe the bigger field which I showed. So now here, would you say there is some length scale buried here? Okay, so in my language, when you are doing modes and k and so on, you also find the specific typical length scale, right? Power spectrum, you have your power spectrum going this way, so this way. So here in this way of doing, just by the spectral property, the first scale, length scale that I introduced, that we can read out from the spectral properties is sigma 0 by sigma 1. What is that quantity? You can see here that visually intuitively you know there is some spread over which there is some, the red color for example is extending all the way up to something. So sigma 0 by sigma 1 gives us the typical size of structure. What do we mean by structure? I will come in the next part. Then you can, the next one is sigma 1 by sigma 2. That is also a length. So that again you can ask, what does that give? What is that information? So that information is between, for example, between one peak and the next peak, there is some typical size. Okay. So, or between the two, let's say low density regions, there's some length here. You can calculate this. Take any two pair of low density region, find out what is the distance between and average it over your entire region. That gives for you a typical length. So, like this, you can define a hierarchy of length scales. Unfortunately, in my lectures, we'll use only one, but remember that when you are doing your research, and you may find it useful to use higher order lengths. Okay? Yeah. Yeah.
RC has one value that should be had earlier
RC has one value for one realization.
for one reason.
Yeah. Because sigma 0 and sigma 1 are properties. So to fully answer your question, I need to define the homogeneity in isotope.
Sigma 0 is defined
At each point, exactly.
when we divide
Yes.
at each point in RC as earlier peak.
What does it mean? Yeah. Then we go to the next slide and you ask me again. Okay, because I need the next two concepts. Okay. So let's look at a few special properties which are important, which we usually, when we are doing cosmology, we take for granted and do not question. Let's write them down nicely. And so we assume homogeneity and isotropy. We are used to thinking of Einstein's equations being homogeneous and isotropy. Mu is written in that particular form. So now, in the language of random fields, all the fluctuations of our matter distribution, 21 centimeter, MB distribution, what does it mean for the field to be homogeneous and isotropic? So it means basically that the language in which you say translation and rotational invariance, positions and directions are equivalent. The mathematical way of putting it is that the probability of the variable, a random variable f at xi, the random variable, is the same as the other field component random variable at any 2 points. Xi and xj can be any two random variables. They have the same probability. That is the meaning of this homogeneity and isotropy. Then the next point is that, so that's why I put small p, the normal p, okay, not the curly p. Then the endpoint correlation functions. So in general, if you have x1 and x2, which are position vectors, dependence of the correlation function of the field. This is not sigma, but of the field. That will depend only on their specificity. Okay, so this is the meaning of the homogeneity and isotropy.
Because the first point is homogeneous.
Yeah, first point in homogeneous. So here, if it is homogeneous, you will have to write it without homogeneous. So instead of, let's say, 2-dimension 4 variable dependence of the correlation function, you will have only 2 variables. And so your degrees of freedom get reduced. Okay, so the next important thing to answer your question is ergodicity. And so far, whatever I have described is, I have a field phi, then I have random variables at different points, and there is a general description. Now, and we have ensemble expectations. All those brackets are ensemble expectations. But in our data, we don't have access to ensemble expectations. Or if you are simulating, yes, you simulate as many as you like, you have the ensemble. but in real life we don't have. So we need a way to obtain our ensemble expectation values, approximate way, and that is to say that okay, the ensemble expectation values can be equated to volume average. Okay. And what allows that? Theoretically, what allows that? What allows that is that okay, at this point my random variable is taking different values, and at this point also my variable is taking different values. The algorithmicity is saying that if I take some large enough volume and I have different number of points, then all the range of values at any given x, the range of values that are allowed for that random variable will be realized at different points. That is the underlying assumption we make. We do this. So all the quantities that you are power spectrum 21 centimeter or you are calculating them as volume average. Okay. All right. So now the next point is that the derivative fields will inherit the properties of the field. So here again, for people who want to be very clear about assumptions and so on, this ergodicity, whether we are allowed to do this, this is proven only for Gaussian fields. But in cosmology, we are left and right. 21 centimeter is highly non-Gaussian, and we are again still doing. So remember that it's an assumption. Okay, it has, at least mathematicians have proven that this can work. But we have no other way to proceed. Okay, if we do this. So let us. Okay, so I think this is my last slide for introducing you to the random field concept. These are all things that you have used, all know, but I just put them together in a form so that because I need them later. I'm going to switch gear now. We'll talk a little bit about the geometry and topology. Okay? And finally, later, we'll combine it. Okay, so the geometry and topology, let's just use the word morphology is used in so many contexts. So I'm going to use it here to mean geometry and topology, basically different structures and their shapes and size and so on. And I'm going to quantify this. Okay, so the first thing I need is to define what I mean by a structure. When we are dealing with random field, it is a function. So what do I mean by a structure there? To reach there, let us first define what I mean by a structure. So what I mean here is that it's a compact subset of some underlying space. So let's say two-dimensional space. I am only interested in some points which are epsilon close to each other, a compact subset of points. That is what I mean by a structure. So symbol, let us introduce the symbol Q to mean structure. So this is, from now on, I'm going to do only two-dimensional. My underlying space is R2, two-dimensional space, flat, that also. And later, I will generalize to here, and I will tell you exactly what is the UT level. So everything now is two-dimensional flat space. Okay, so this partial Q is the boundary of this is my structure, right? Okay, so by looking at this, you immediately have some concept of a morphology of this structure, right? In two dimensions, you may say, okay, what is the area covered by the structure? What is the perimeter of the boundary? The third point is you can say, okay, in my picture, I see one structure. In count. So these have dimension of L square, L1, and L0. You can also see that there is some sort of a intuitively you see there is some notion of elongation. So there is some direction and elongation. You want to quantify this. These are easy. These we have been doing it school onwards. You know, calculate area and perimeter. The count also here, without doing any mathematics, you can say it is 1. But the purpose for our purpose is that we will have some random field, we will have some structures, and we are not going to go and count one by one. We will have some mathematical way to do the calculation. We need to define, express this counting in a mathematical formula so that we can calculate it given any data. And similarly, this orientation. So this is like aligned this way. So these are all questions that you can think of. Similarly, in 3 dimension, if this were 3D extended, you can say there will be volume, surface area, and in mean curvature, the integral, then count, similar. These are the questions that we are interested in. Okay. So let's do this. So in order to build up the methodology for quantifying the morphology, if let me just choose the coordinate system, and every point on the body, on the structure, will have some position vector. It's up to me what coordinate I mean. Then you can define at every, on the surface, on the perimeter boundary, you can define a normal vector. It's obvious, intuitive, right? It's a normal vector. And there is related to that end, there is a tangent vector. The tangent vector is not unique. It can be either this way or it can be this way. You decide which direction I will do. So there are these three things. Then you can have d2x. Later I will use dA. There is an infinitesimal area element. There is infinitesimal arc length. On the boundary, you can take small units and you will denote that by ds. These are all quantities associated. Now, there is a quantity called geodesic curvature here with the boundary, the perimeter. What is that quantity? That quantity is called kappa, denoted by kappa. It is the rate at which, this partial should be g, because ds is the arc length. So this is, you have the unit tangent. You can ask the question, what is the rate at which the tangent is turning around the perimeter? Have a tangent vector. So you can see here, let's compare this point, maybe this point, or maybe this point is good. So here, the tangent is going to turn very fast. And you change a small amount of arc length, tangent will turn. So that is region of high curvature. Okay, that's a geodesic. So when this is high, it's going to be kappa is. And similarly here, on the other hand here, this is relatively flat. It will not turn as fast. Value of kappa out. So you can define this quantity called geodesic curvature. The definition. So these are quantities associated with this. So now, yeah.
You have a sharp.
Yeah.
So in that case,
It will not be defined.
it
It won't be defined. So the assumption here, because this is, if it is sharp, then it won't be differentiable.
there are two types.
On this side one way, on this side one way, it won't be, there will be a jump, discontinuity in kappa. So the assumption here is that all the curves that I get will be smooth. My structure has a boundary which is smooth. Okay? And that is associated with the smooth field. Or they are all differentiable. Okay. So now let us write down these. This area is of course integral over this. Perimeter is integral over the boundary. Now the count is, but so the symbol is, I'm introducing the symbol chi here. If you integrate kappa over the boundary and over the boundary with the ds as the line element, then with the 2 pi in front, 1 by 2 pi in front, this gives me 1. Okay. This you can work out as exercise. Maybe in the tutorial I will give a sheet and this will be one of them. So, of course, trivially you can show it for circle. It's also. So this is one. So this is a simple statement of what is called the Gauss-Bonnet theorem on flat space. To ask here some question. Okay, so there are these three quantities, so you can count by doing this. So here is your method. Now let's look at elongation and filamentarity. So there is a slight elongation here, and for that, if one can define a quantity called f, which is perimeter square minus 4 pi area divided by sum of the two. Okay, so where does this come from? So this quantity was introduced by the paper by Varun Sani et al. Around 1998. And then Somnath also had a paper maybe for 2D. For this particular case, Somnath had a paper on this and applied to large-scale structure data to see whether matter distributions are elongated. So that is where it was defined. So now what is this? How does it capture the elongation information? You can ask. So think of a loop. Just think of a thread which is closed as a loop. So you can, given the length of the perimeter, you can arrange it. What are the different ways in which you can arrange the so that the area enclosed within changes. Perimeter remains same, but the area is changed. So if you are arranging it as a circle, it will have certain area within. Now that area, it's very easy. You can trivially work out and show that p square equal to 4 pi a then. So in that case, for a circle, this f will be 0. Now if you squish it so that it becomes an ellipse, then this will be, it will go towards 1. Okay? And it will go towards 1. And so you have something called the isoperimetric ratio, which is a ratio between the perimeter and A for any loop. And that ratio is highest for a circle, exactly equal to 4 pi. And so that is what is working here. Okay? So that way this quantity, filamentarity, it will provide information. Now for orientation, these are not enough. You have to do something else to get the orientation and anisotropy information. Okay, so yeah.
This one. Perimeter.
Yeah.
Therefore,
One structure.
almost
We need many structures. Yes, I'm going to come to that. So again, this is a very simple. This is what is called a simply connected structure. Okay, that means that all points are neighboring, all points are close to each other, and there is no hole in between. So we'll deal with one is okay. So now the next is something called a doubly connected structure, and that is a structure which has a hole in between. That means some regions here are not included in your structure. So here when we are doing, what is the change from the previous one? The change is that the boundary is now, there are two loops. That's the boundary. That's a change. Now if you're calculating area and perimeter, they will simply add up. Right? They're all scalar quantities. But now what happens to the count? Count does something different. So count will become integral over this loop and over this other loop. Now there is a fundamental difference between this and this in the kappa. And there will be a sign difference. This is a normal event. So that's what, so this part, this loop, I have taken it out and made the picture here to show that the normal is now in the opposite direction, whereas here it was pointing outward and inward. There's a difference, and because of that, there is a sign. If I'm calculating chi, the count of the structure here, my count will be 1, 1, so I will get 0. Now, so I will get this. So, okay. Similarly, now for the filamentarity, you can use the same thing. You have now the option of saying, okay, what is the filamentarity of the inner loop and the outer loop? Those are things you can play around with, but the definition remains the same. And again, we don't know what the orientation. Now you can have, so here this is the doubly connected, then you can have triply connected and multiply connected. So single structure with many holes in between. This is the hierarchy of shapes possible. So Now let me just introduce some terminology. You know that out of these, you know that these are geometric quantities. That means if you deform your structure a little bit, the values will change, but the counts will not change. The topological count. So just to introduce some terminology, if I count the curves independently, each curve, then the connected, this is one connected region, this is also one connected region. So that can be counted by looking at how many curves are used. Then for the holes are these kinds of curves. There are different, the curve, nature of the curve is slightly different. So you can also count. So the counts of the connected regions are typically called the Betti numbers. So connected regions, if Betti is 0, use the symbol NC for a connected and number of holes for NA. So you given any structure, you can define, and chi will be there alternating sum. So here, for this one, NC is 1, NH is 0, chi is 1. Similarly here, NC is 1, NH is 1, chi is 0, and so on. You have this, you can do now generally. Okay, I'm a little slow on time. Can I move on? Okay. So maybe I'll do this alignment and my time is still. Yes. Okay. So now what we want is we want to deal with many structures. And when we are given many structures, typically we'll have some example like this. And so the area, perimeter, etc. will get added up. And the filamentary can be defined for individual structures or average individual structures. It's up to you. But now there is a collective property now which arises, and that is of alignment. So you can ask, is there any alignment between these structures? So we want to quantify them. Whatever we have defined so far, Betti number and so on, they are not sufficient to define them. So we need a little bit more maths to define them. Of course, if you are able to identify individual structures with an ellipse and say, okay, the ellipse is oriented this way, then you can do it. But there's a very inelegant, some way to do it. We want something nicer. Okay. So, before I move on to that, the names in Minkowski functionals is now appearing. So the area, perimeter, and Euler characteristic in 2 dimensions. Oh, Euler characteristic. So Betti is clear. Euler characteristic is the difference between all of them. Right? It is form of structure, but now I made a distinction between 2 kinds of structure. One is a whole, sense of the value, and the other is connected with it. And Euler characteristic of that is the difference between them. That is Euler. Yeah. Yes. Yeah. Why we need Betti? Because when we are doing, let's say we are applying it to random fields, then you are throwing away some information. So they are independent degrees of freedom in general. So there is some correlation, let's not worry about that. But there are 2 different independent degrees of freedom. And if we are using their difference, we are throwing away 1 degree of freedom. So we lose some information. That loss of information will be basically 1 by square in this case. So it is when we are trying to extract as much information as possible. This can become useful. Well, in 2D, these are only 2. In 3 dimension, structures are much more complicated. You have three kinds of Betti. Is that the question you are asking?
If it is 0 Betti 1 and Euler, you could just do it 2 of them.
Yeah, we can just do it 2 of them. So historically, so this is easier to calculate. Okay, so this has been chi has been used as part of the Minkowski function. Whereas this is relatively new. Separate Betti number is relatively new. It is notoriously difficult to calculate theoretically.
For
Yeah.
structure is
It's enough. Yeah. For one structure, simply connected as one. But we are going to deal with a collection of is the point here?
it is not clear. One
Okay. So Betti zero is this structure for this example. This is one connected region. Points are all connected. Yeah.
Maybe if you think of that thing repeated same thing. Maybe
Oh,
that is the condition.
okay. Here, let's see. This is suppose I'm given this. Betti number will be 1, 2, 3. Betti zero will be 1, 2, 3. Number of holes will be 1, 2, 3.
also is 0, 1, 2.
There's zero here, but I will be considering this as my structure, a set of my whole structure set. For that, I will calculate what is the Betti number, and for then I will say okay 1, 2, 3. That way, I'll count whichever individual structure has
For the full structure,
Yes. Is that fine now? So this is just terminology. So Minkowski functionals are these three: area, perimeter, and Euler characteristic. And the reason for Euler characteristic being simpler to calculate is this: that the formula does not distinguish between the two kinds of boundaries. So given a field, you can just calculate kappa, integrate, and that gives you. Okay. Now, these quantities, as by definition, they are invariant under translations and rotations. Right? You can look at the formula, all of them, they are scalar quantities. So you will also find the word scalar and Minkowski functional being used. So now, as for these, the elongation and the filamentarity information can be obtained from them, but anything to do with direction and alignment, so we have to use viewer statistics. Okay, maybe this is a good place to stop. I don't know. Can you guys still stop some more? Yes. Okay. Then, so let us look for the alignment. Yeah. W2. Yeah. Actually, it depends on, this can be written down as Betti 0 plus Betti 1. Yeah. But numerically, we can calculate, and we have calculated and used it in data, but we cannot relate it to random fields. Okay, I'm working on it. It's very hard. Yeah. Unfortunately, I cannot answer this. It goes beyond my maths knowledge. They put a citation for Adler. That's a book. Geometry random field. Okay, so now let us define what are called Minkowski tensors now. So we are going to extend the definition of Minkowski functionals, tensorial quantities, using the normal vector. Okay. So here there is this class of objects. Let us slowly look at them. There is a lower index 0, 1, and 2, and there are upper index m, mn, and mn. So mn are integers 0, 1, 2, positive integers 0, 1, 2. And here on the right hand side, this is an integral, this is an area integral, and this is length integral over the boundary, also length integral. So this is constructed from the tensor product between the position vector and orbital. And we are going to be interested in M and N being 0, 1, 2. So this is just a set of formula. Let us write them out and see how we can use them. Okay, and the tensor product is defined as between any two vectors A and B. It's a symmetric tensor. So A cross Bij is AI Bj plus AJ.
What does this
One
component?
What does this? Sorry, yeah.
What does this? If W A is 0, then W becomes the total area. W is 0.
Yes, yeah. We'll see that in the next slide. Is that okay?
What is Rn?
Rm is to the power m. R
To the
cross
power.
R cross R. So we'll only be interested up to 2. And we'll not use most of them. We focus on the ones that have direction. Now, as you were saying, we can write R to the power 0 is just integral dA, that is the area. Similarly, here m and n, if they are both 0, that is perimeter. And if this is 0, 0, that is just the Euler characteristic. So the rank 0 are being recovered from this formula as the scalar Minkowski functions. So now the question is, if we look at the tensorial, say rank 2, rank 1, we are not going to be interested in because that is we are dependent on coordinates. We want to look at coordinate free, coordinate independent or translation invariant Minkowski tensor. So rotational invariance is because that's what it is. So we'll look at those ones. Okay, so here are they. Rank 0 are these 3. Then rank 1 just ignore. And rank 2, you can classify them as separately. The ones which contain R, they are going to change with coordinate translations. We won't be interested in those. Let's look at the translation invariant. And those should not have R. And among those, there are 3 which are independent. Okay. And I'm going through this fast because I will only be interested in this red one. So there is one which has the dimension of area, and that can be shown to be, it reduces, it's the basically area times identity matrix, and the count also can be shown to be Euler characteristic times identity matrix. So there is only one left, and we will examine this in detail. Okay, W1, 0, 2. You can see from 2, 0, 2 will be n hat cross n. And there is index 1 here, so it will be integral n hat cross n ds. There is no kappa on, so this is a new one.
When we are defining square or R,
Yeah.
it's R with square cross R with square.
Yes.
That is 0.
Yeah. So, yeah.
So there is no W20.
Okay. So now there are these 3. Now, as I have just explained, the trace of one of them is trivially area, so there is no new information. The trace of this W2 last one is a characteristic, so no new information. The trace of this W102 and had cross and that gives me W1. Again, that's very trivial to do, and had cross and had because they are unit vectors, 1 1 component and 2 2 component. That adds up to this one. Okay, so we want to examine this in detail. So maybe I will go till here and then I will pause. Okay. So let us see what is this new information that is. So what I have done here is I did not write it as in terms. So it will in general be a 2 cross 2 matrix, correct? Because it's a second rank tensor, I can write it as a 2 cross 2 matrix. And what I have done here is I want to express the symmetric 2x2 matrix in terms of some basis of rotational invariant. This is in just like sigma matrices. The complex one will not be here because it's real matrix. That is why like this, and so there are 1 to 3 degrees of freedom. Symmetric 2x2 3 degrees. Okay. Then so that means clearly this has shape information. And if this matrix is identity matrix, for a given structure, I calculate and I find that it is identity matrix, it will be, it is no elongation. It's a isotropic structure. But if these G1, G2 are non-zero, then it will be elongated. So in order to this is so any 2x2 symmetric matrix, you can write it as a linear combination of tau G1, G2, 3 degrees of it in terms of sigma matrix. So tau, so you can imagine writing this as tau times identity matrix plus G1 times 1 minus 1 0 0 and G2 times 0 1 any matrix.
Sigma matrix is the same.
A Pauli matrix. Okay, so so we can always do this, and or you can look at the eigenvalues under one and I have this matrix in general G2 non-zero, so I can rotate, make it identity. I make it into a diagonal matrix, and the two eigenvalues. Let's assume that. Oh, sorry, this should be 2. So in my notation, let's say lambda 2 is the larger one. Then I can define a quantity called beta, which is their ratio. If the ratio is 1, the structure is isotropic, and if it deviates from 1, it has elongation. Then I can also track the information of the orientation. So with my chosen coordinate system is a structure like this, like that I can extract by defining this one. This is exactly how you do when you have QU polarization tensor. These are the two quantities that you've given this. To simplify, I call it contour Minkowski tensor. The generalization of the contour length parameter. And so these are these new information is being presented. So there are 3 information. One is tau, 3 degrees of freedom, tau, which reduces to the perimeter, and the orientation and the isotropy information. Of course, beta is independent of coordinate, but phi will depend on whether you rotate your coordinate system. That is dependent on the coordinate. Okay, so there is this shape information. Now you can ask the question: how does this beta differ from the filamentality? Are you just repeating the information, or do you get some new information? Is it useful to you? So those kind of questions we'll look at it more. My next lecture is tomorrow, right? Okay. Any questions from you?
We are defining alignment.
Yes, I will define.
We have not yet defined.
I have not defined alignment. This is we have to look at individual structures, then only we can do collection of structures. Tau G1, G2. So tau is a trace. So if I give you a 2x2 matrix, you can always write it as this linear combination in terms of Pauli matrices. You can do. So whatever is the coefficient of the Pauli matrices, tau G1 and G2.
Pauli plus.
Pauli plus identity. I am assuming back into the
The tau is the coefficient of identity.
yeah. How is the identity?
One is the coefficient of 0.
The game you can play is somebody gives you a structure, look at the boundary, and you calculate this W2, W1, 0. You can calculate. But if you given a structure, you choose a coordinate system and say this point is R or something, R. you calculate. Then, given that you approximate, now you can split this. So the idea is that if G1 and G2 are turned out to be 0 for your structure, then it is a proportional coordinate that will be like an isotropic structure. Well, for what the remaining of my lectures, I will not use G1. I've used this for some other paper where I was doing some M4 But it's a nice way to look at to write the matrix in terms of basis functions, right? Just like you do the power of x. Okay, are you convinced? Okay, take an array, and I am aligning it in such a way that the QP, the major and semi-major minor axes are aligned to the coordinates. Make my coordinate. And put this as a coordinate. So if you have this, then you can calculate. It is easy to calculate actually. So each point will be r tan theta by a or b. So there will be a variable theta which will be labeling the contour, and you can calculate explicitly what is the distance. So what you get is that so these off diagonals are 0, turn out to be 0, and that is because this is nicely aligned. And these two, there are two coefficients here, they look same, but P and Q they are interchanged. Q and P are there. In terms of the semi-major axis, semi-major minor axis QP, you can calculate this. It will be a function. And the expression is here. So it is not an exact expression, but you have to do the integral, and the integral answer depends on what P and Q. So no, if you have P and Q exactly equal, then this will become identical. These two will become same. And same means there will be the tau. And so what it's telling you is that if this structure is isotropic, then W202 will turn out to be proportional to identity matrix. If it is not isotropic, you will have difference between the two others. Okay, that is the interpretation. Now you can say, okay, let me rotate my ellipse and put place in this way. Then your calculation will be more complicated. I will not give that exercise. You do numerically. That will tell you the orientation, the angle will be captured by that variable. This is how it's okay. So I'll go